Hi everyone, this video is about Lagrange's theorem and the class equation. Lagrange's theorem and the class equation are both important results in group theory that have to do with counting within finite groups. And both of these theorems involve partitioning a group into equivalence classes. So we begin with Lagrange's theorem, and so we start with a finite group, G, and a subgroup H, and the result tells us that the size of H will always divide evenly into the size of G. And we can write that as an equation like this. We can write the size of G is the size of H times something, and that something, here denoted by G:H in brackets, has a name. It's called the index of H and G. And what it does is it counts the number of cosets of H in G. And it doesn't matter whether they're right or left cosets, because we know that the number of left cosets is exactly equal to the number of right cosets, as we discovered in the last video. Now, speaking of the last video, this result, Lagrange's theorem, should have some ring of familiarity, and if so, it's because we essentially proved Lagrange's theorem in this last video. So you might remember that starting with our group capital G, we can put this equivalence relation on G, and we saw that the equivalence classes under this equivalence relation, which must partition G, are actually the left cosets of H in G. And furthermore, all of these cosets have the same size. They're all of the same size as the subgroup H itself. And so what that means is that we're partitioning G into these cosets, each of which have the same size, namely the size of H. And so if we want the size of G, we just take the size of H times however many left cosets there are. So let's look at Lagrange's theorem in the context of an example. So we're going to use one of our favorite examples, that is the symmetric group, G equaling S3, which we've looked at in several prior videos. And we're going to look at the subgroup H, which has just the identity and this element G of order 2. So remember, in the symmetric group, F cubed and G squared are both equal to the identity. And if you take F times G, that's always the same as G times F squared. Okay, so let's look at the left cosets of H and G. And one of those is just H itself. We can also compute F times H. So that means we're taking everything in H and we're multiplying by F on the left to get this. And then we also have F squared times H, which yields this. And now we could go on and compute other left cosets, but those cosets would just give us repeats of the three cosets that we have here, right? So notice that these three cosets together, they are disjoint, and their union gives all of the group G. Now similarly, there are three right cosets, H itself, and then H times F, where we're multiplying everything by F on the right to get this. And then here, where we're multiplying everything by F squared on the right to get that. And once again, we could compute more right cosets, but we would just be repeating the cosets that we've got here. Again, the group G is the disjoint union of these three. So here, whether we're talking about left cosets or right cosets, the number of cosets of H and G is 3. It's the number of distinct cosets. And the size of G, which is 6, can be written as the size of H, which is 2, times the number of cosets of H and G, which is 3. Let's now look at a few consequences of Lagrange's theorem. Throughout in this discussion, our group capital G is going to be a finite group. So the first result says that if you start with an element in this group, then the order of that element must divide the order of G. And further, that if you take X and you raise it to the size of G, the result will be the identity. So anyway, remember that the order of X is exactly equal to the size of the cyclic group generated by X. But Lagrange's theorem tells us that cyclic subgroup must divide the order of the group itself. Now, when we take X and we raise it to the order of X power, we're going to get the identity. And since G is since the order of G is a multiple of the order of X, the same will be true when we raise X to the order of G power. So that addresses the first bullet point. The second bullet point essentially follows from the first. So if the order of G is prime, and you have some non-identity element X living within G, then the order of X is bigger than 1, and it divides the size of G. But the size of G is prime, and so that forces the order of X to be exactly equal to the size of G. So if the order of X is equal to the size of G, then that means that this cyclic subgroup generates all of G. So that means that this group G is cyclic, and it's generated by any X within G that's not the identity. So you can also use Lagrange's theorem to understand groups of small order. Okay, and here we have a little table that gives us sort of the number of essentially different groups of various small orders. So when n is 1, the number of groups of order 1 is just 1, right? I mean, it's just the identity, the trivial group, right? When n is 2 and 3, well, both of those are prime numbers, and we know that groups of those orders must be cyclic. And so that means that these are essentially Z2 and Z3, both under, modular addition, right? For order 4, it turns out that there are only two groups. There's Z4 and another group called the Klein 4 group or the Veer group. And what you should do if you feel like you're up for a challenge now is to pause the video and just draw out a group table with E, A, B, and C, and see how many possibilities there are. And I think you'll be able to, just using elementary properties of groups, determine there's really only 2 ways to fill in the table. 5 is a prime number, so we know that a group of order 5 must be cyclic, and so that's really Z5 under addition. 7 is also prime, and so we know that there's only one group of order 7, that is the cyclic group, Z7. And then that leaves groups of size 6. Now it turns out that there are exactly 2 groups of size 6. So there's Z6, which we're familiar with, and then there's also this symmetric group, S3. And you might be wondering, well, how do we know that those are the only 2? Well, it turns out that we're going to do an exercise in this section that uses Lagrange's theorem to help us see that those are really the only 2 groups of order 6. So I've assigned an exercise in section 10, namely exercise 10.14, where we're going to, or you're going to prove that there are really only 2 groups of order 6, namely the cyclic group Z6 and the symmetric group S3. And in this slide, we're going to get a start on that exercise. So to begin, we're going to let capital G be a non-cyclic group of order 6. And our goal through the exercise is to show that this group must be S3. Okay, so the first order of business is to show that this group has an element of order 3. And we're going to argue by contradiction, so let's suppose not. And we're going to let X and Y B and G that are not the identity. Now, what this says, remember that the order of any element in G must divide the order of G itself. Now, since the group is non-cyclic, no element of G can have order of 6. And we're told that, or at least we're supposing, that G has no element of order 3. So the only other possible number that divides 6 and is not equal to 1 is 2. So that's telling us that every element of G would have order 2. Now you might remember from section 3, I believe it is, the homework, there was an exercise that shows that any group where every element is of order 2 must be abelian. So this group must be abelian, and that's going to help us fill out a table like this. So we have EX, Y, and X times Y. So EX, Y, and X times Y. So let's just fill this out. Now, X times X must be the identity because the order of X, and in fact the order of any non-identity element must be, of order 2. So now X times Y is just XY. Now that is not the identity because we're assuming that X and Y are distinct, and X is its own inverse in here. So X times Y is not the identity. X times XY is just Y. Y times X is equal to X times Y because, as we explained a little earlier, this group is forced to be abelian because every non-identity element has order 2. Y times Y is the identity. Y times XY, again, if you move the Y around, you get that that's just X. And then similarly here, this gives us Y and X. And then finally, anything times itself is the identity. So this thing is a subgroup of G. But that's impossible because its order is 4. But 4 doesn't divide evenly into 6. And so that contradicts Lagrange's theorem, right? The order of every subgroup must divide the order of the group. So what that means is that our original supposition, that is, we suppose that G has no element of order 3, that must have been incorrect. So G must have some element A of order 3. Okay, now we're going to go on to part 2, and it tells us that we should pick some element B that's not in the cyclic subgroup generated by A. Remember, A has order 3, and so that means that the cyclic subgroup generated by A would be just EA and A squared. So because the order of capital G is equal to 6, there has to be something in capital G that's outside of this cyclic subgroup. And we're going to call it B. We're just going to pick something outside of there and call it B. And what we're claiming is that this list, EA, A squared, B, AB, and A squared B, those are the distinct elements of G. So all we need to do is show that they're all different, right? Because we're already told that G has 6 elements. So we just need to show that these are all different. So we know that EA and A squared are all different from each other. B can't be EA or A squared because we have chosen B not to be in the cyclic subgroup generated by A. So these 4 right there, we know that they are distinct. So what about AB, the next element in the list? So if it were equal to B, then by cancellation, that would imply that A is equal to the identity, which doesn't happen, right? A is not the identity. If AB were, say, equal to A squared, then what? That would say, by cancellation, that B is equal to A, which again can't happen because B has been chosen not to be in the subgroup generated by A. And now what if AB is equal to A? That again says B is the identity, which again, B can't be in that subgroup generated by A, and E is in that subgroup. And let's see, what else do we have? What if AB is equal to the identity? Well, that would say that B is equal to A squared. And again, B has been chosen not to be in that subgroup generated by A. So that shows that this element AB cannot be any of the prior things. So similarly, you can make similar argument. So similarly, A squared B is not equal to any of the things that are in the list prior to it. EA, A squared, B, or AB. And so what that means is that all of these 6 elements in the list, that they are all distinct. And so that must account for every single element in G. Now we introduce a completely different way of partitioning a finite group G. And this begins with defining a relation on the group. So we say that A is related to B exactly when B is what we call a conjugate of A. So that means that B is obtained from A by multiplying on the left by X and on the right by X inverse for some X in G. So in the next couple of examples, we're going to just compute some conjugates. So the first example says that we are to compute conjugates of 2 inside the multiplicative group of non-zero real numbers. So what that means is, well, we start with 2 and we multiply on the left by something and on the right by its inverse. Now, since we're in the multiplicative group of non-zero real numbers, that's X times 2 times whatever the reciprocal of X is. Now, in the non-zero real numbers, we know that 2 commutes with everything, right? In fact, this is an abelian group. So since 2 commutes with everything, we can move the 2 to the, interchange the position of 2 and X. And we get 2 times 1, which is just 2. So the only conjugate of 2 is 2 itself. Right, so the only conjugate of 2 is 2. Okay, and really sort of the reason for that is that 2 commutes with everything. In this group of non-zero real numbers under multiplication. Okay, so that should tell you, say, that in an abelian group, if you start with an element in that group, the list of conjugates is not going to be interesting. It will just consist of that element you started with. Well, why don't we do another example where we compute conjugates of an element in a group? This time our group is a more unfamiliar object. It's the group of quaternions. So this is a group of order 8 where the identity in the group is 1 and the elements plus and minus 1 commute with everything in the group. We also have these other relationships, for instance, I squared, j squared, k squared, and ijk are all equal to minus 1, and the square of minus 1 is equal to 1. So in this problem, what we want to do is compute the conjugates of I. So there are some other relationships among I, j, and k that we can determine from these existing relationships, and they are I times j is equal to k, j times k is equal to I, and k times I is equal to j. So now, with that in our hip pocket, let's go ahead and compute a few conjugates of I. So what that means is we're going to take I, and on the left we're going to multiply by something. Like, for instance, let's multiply by k on the left. And then we're going to multiply by k inverse on the right. And we're going to see what we wind up with. Well, we know that in this group, k inverse is minus k. And we know that k times I from over here is equal to j. So that is minus j times k. But we know from the left panel here that j times k is I. So this time, instead of just getting I in return, we get minus I, which is something different. So we can conjugate I by some other group element. I mean, for instance, if we do minus 1, for instance, we can take minus 1 times I times minus 1 inverse. That's minus 1 times I times minus 1. Right, minus 1 is its own inverse because minus 1 times itself is 1. And remember, minus 1 commutes with everything in this group, so we can bring the minus 1s over to the left and leave the I on the right, and that just returns I. Now we could continue doing this for, the other 6 elements of Q8. And what you will find is that the conjugates of I are just I itself and minus I. So one thing this tells us, because this set has size larger than 1, this means that there is at least something in the quaternions that I does not commute with. In particular, I and k do not commute, and that's why the conjugate of I by k is something other than I. Okay, here we've defined this conjugation relation, and it turns out that it's an equivalence relation on G, and here we want to prove that fact. Now we remember that the relation is as follows, that A is equivalent or related to B exactly when B is equal to XA, X inverse for some X in G. Okay, now to prove this relation is an equivalence relation on G, remember there are three things we need to do. The first is we need to show that the relation is reflexive. Right, so any A is equivalent to itself because you can always write A as, E times A times E inverse, right? So the second thing we need to show is that the relation is symmetric. So let's suppose A is related to B. We want to show that B is related to A. So anyway, A is related to B. That means that B is XA, X inverse for some X in G. And that means that if you multiply on the left by X inverse and on the right by X, you get X inverse B times X is equal to A. And hence, A is equal to Y times B times Y inverse, where Y is equal to X inverse. And that tells us that that B is related to A. And that's what we wanted to show, right? We started with A being related to B, and we wanted to show that B is related to A. So that's our symmetry. And then for transitive, what do we want to do? We suppose A is related to B and B is related to C. Then we know that B is XA, X inverse, and C is equal to YB, Y inverse for some X and Y. And so what does that mean? Well, all we're going to do is take this equation and substitute in this expression for B. So C is Y times X times A times X inverse times Y inverse. And that is YX times A times YX inverse. And that says that A is related to C. And we're done with the proof. Okay, now that little piece of drudgery is important because this relation that is now known to be an equivalence relation, its equivalence classes are going to partition the set G. So that means that we can write G as a union of these disjoint equivalence classes, much as we did in the last video. Well, let's now partition a group into the equivalence classes that we get from the conjugacy equivalence relation. So the group in question this time is going to be the dihedral group D4 we discussed in an earlier video, and it consists of F's and G's, where we know that F to the fourth is the identity, as is G squared. And the relationship between F's and G's is that if you take F times G, that's the same as G times F cubed. Okay, so here I've presented you with the list of the conjugacy classes. Let's see a little bit about how they might be computed. So for every element of the group, starting with the identity, we're going to want to compute the equivalence class containing that element of the group. So we denote that with a bar over the top. So E bar means that we're looking for all of the conjugates of E. That is, all of the things that are related to E under this conjugacy relation. Now, you might notice that if you take a conjugate of E, well, E commutes with everything. And in particular, it commutes with X inverse. And what you wind up with is just E. And so every conjugate of E is just E itself. Right? So that takes care of this. Now, a similar thing happens with F squared. If you look at all of the conjugates of F squared, what happens? Well, F squared, it turns out, commutes with every single thing in this group. And so if you take X times F squared times X inverse, just like in the previous calculation, you can slide the F squared past the X inverse, and what you wind up with is F squared. And so the conjugates of F squared are really not very interesting. You just get F squared back again. Now, finally, something interesting happens when you consider F, right? So we want to look at the conjugates of F. So let's first take the conjugate of F by itself, right? So if we take F times F times F inverse, that's F times F times F cubed, which is what? F to the fifth, but F to the fourth is the identity. And so this becomes just F. But now if we conjugate by G, so we're going to take G times F times G inverse. What is that? Well, that's G times F times G. Remember, G is its own inverse. And F times G, remember, is GF cubed. And therefore, I can replace FG with GF cubed. But G times G is the identity. And so this gives us just F cubed. So F cubed is also a conjugate of F. And it turns out that if you take the conjugate of F by every other thing in the group, you're going to wind up with one of two things. You're either going to get F or you're going to get F cubed. Now the same thing is true for G. So you can make a similar computation there and again there. And maybe it would be a good time, if you want to pause the video and see if you can make those calculations. All right, so therefore, we have the dihedral group written as a union of these classes. It's a disjoint union, as we would expect, because these are equivalence classes, and therefore they must partition the group. So another way to write this down, notice that E and F squared have only one thing in their equivalence classes because they commute with everything in the group. And you might remember that the stuff that commutes with everything in a group is called the center of the group. And that is denoted by a Z. right? So that's the center of the group. And then you have these other classes, F bar, G bar, and F, G bar, that each contain more than one element. That last example suggests a theorem. If we take a finite group, we can break it into conjugacy classes. Some of those conjugacy classes are going to be of size 1. And if we take all of those and lump them together, that gives us the center of the group. But then we will have left over some distinct conjugacy classes of size 2 or larger. We can use those to fill out the remainder of our group G, where the union that's given here is disjoint because conjugacy classes serve to partition a set into disjoint pieces. Now, this first bullet has something to say about the size of G, right? So that means the size of G is the size of the center together with the sizes of all of these conjugacy classes that are of size 2 or larger. And this latter equation that involves the size of G has a name. It's called the class equation. Now, we could just brush our hands and walk away, but there is a way to further refine the class equation, and it involves these centralizer subgroups. So you might remember from a week or two ago, if you have an element little g in your group capital G, and you consider all of the things that commute with little g, that forms a subgroup called the centralizer subgroup associated to that element little g. And it turns out there's this theorem that says that the number of cosets of a given centralizer subgroup in the group G is equal to the number of elements, there should be bars around this, equal to the number of elements in the conjugacy class determined by A. So if you incorporate that theorem into the class equation, what you wind up with is this, that the size of G is the size of the center together with the indexes of all of these remaining centralizer subgroups. Let's now prove the theorem at the bottom of the previous slide. So this is the theorem that says that if you have a little a in capital G, then the index of the centralizer of A in G is equal to the size of the conjugacy class of A, meaning that it's equal to the number of conjugates of A in G. So to do this, we're going to define a function that we'll call f, and it's going to take left cosets of our centralizer subgroup, and it's going to send them to conjugates of A. And we're going to define it like this. We'll take f of a left coset of the centralizer subgroup. It's going to be sent to about the only thing that we can think to send it to. And that is this conjugate of A. Now, if this function is well-defined, then it's going to be onto, because remember, x can be anything in G, and that means that we're going to obtain all of the conjugates of A through this process. So we're pretty sure that this function, if it's well-defined, is onto. So it remains, or that is, it's sufficient to show that f is well-defined and 1 to 1. Right, those are the things that we need to do. Right, now why is that enough? Well, if that's true, then this function will be a bijection, which will mean that the number of left cosets will be equal to the size of the conjugacy class. And that's what we're trying to show, right? Remember this index thing up here. That's the number of left cosets, and this here is the number of things in the conjugacy class. All right. And why is there an issue with F being well-defined? Well, remember that two group elements, X and Y, and they could be different group elements, are capable of yielding the same coset. And so we would need to know that they would also yield the same conjugate in order for this function to be well-defined. So let's take two left cosets and stick them into this proposed function f. And let's suppose for a moment that we get the same output. So that's going to happen if and only if these conjugates are the same. And now moving things over a little bit, moving things around a little bit, this says that y inverse x a is going to be a times y inverse x. So that means that a commutes with y inverse x. So that's true if and only if y inverse x is in the centralizer subgroup associated with A. And that happens if and only if, you might remember from a previous video, that happens if and only if the two cosets, left cosets, of the centralizer subgroup of A by y and x are equal to each other. So the forward direction of this argument shows that the function is 1 to 1. The rearward direction of this argument shows that f is well defined. And that proves the theorem. Here we list just a couple of interesting consequences of the class equation. The first is that if you have a group and its size is some kind of prime power, then the prime must divide the center of the group. So what that means is that the center of this group is, in some sense, relatively large. It's at least of size p. Then the second fact is that if you have a group of order p squared, where p is any prime whatsoever, then that group must be abelian. You'll be proving both of the consequences of the class equation that were given on the previous slide. Now, in one of those consequences, which is the subject of exercise 10.29, so I think this is the one where you have a group and its order is p squared, where p is a prime. And that implies that G is abelian. So in that exercise, there's a little fact that's helpful in completing it. So it says that if you start with a group and an element little g in that group, and you suppose that the centralizer subgroup corresponding to the little g is actually equal to the center of the group, then the group must be abelian. Okay, now the point of the proof, or at least the idea of the proof, is to show that G is a subset of its center. If you can do that, it's already known, of course, that the center of the group lies within G. So if you put those two facts together, that would imply that the center of the group is equal to G. But remember, the center is all the stuff in the group that commutes with everything. And so this statement would be saying everything in the group commutes with everything. And that means that G is abelian. So all we're going to do is show this subset relation right here. So start with an element X in G. We know that little g, being in the centralizer subgroup, together with the fact that this centralizer subgroup is actually equal to the center of the group, forces little g to be in the center of the whole group. And therefore, G must commute with this little x. So that says that X is in the centralizer subgroup corresponding to G because it commutes with this little g. But again, we apply our hypothesis that the centralizer subgroup is equal to the center, and that tells us that X lives in the center of the group. So if you take stock of all of that stuff, what have we done? Well, we've started with this arbitrary element in G, and we've shown that it lives in the center of G. And so we have this subset relation, which is what we were trying to show.